So let's now dive into this concept of efficiency of an engine. And we've used that term efficiency a couple times in the class and we talk about it. And sometimes I don't think we fully understand or not really clear what we mean by efficiency. So let's define this pretty carefully. And when we talk about efficiency, anytime we talk about efficiency, it's really what output am I getting based on what input do I put into it. So if I have a perfectly efficient system, whatever I put into the system, I should get out 100%. Well, if I've got inefficiencies, I know that what I put in, there's going to be something happening in the inside that I'm not going to quite get the same amount out, and that's inefficiencies. So what does that look like in equation form? How do I calculate that? So we're going to use this Greek letter eta to talk about efficiency. So that's going to be my efficiency, and it's basically going to be some output based on some input. So now when I'm talking about an engine, I'm talking about how much power do I get out of that engine. So we'll look at it in terms of power. So this is the output power. Now we can measure that with a dynamometer, and we've done that with the tractor. So we've put a dynamometer on the power takeoff on the back of the tractor to measure what the output is of that tractor. So that's the power output that I get out. That's what's doing useful work. That's what I have available to do something with. Well, what is my input power? Well, the input power is basically the fuel that goes into that. So that's how much fuel that goes in. So now we're going to get back to this concept of how much energy is in the fuel. Okay, a certain volume or mass of fuel has a certain amount of energy, and how much of that fuel, that certain energy content fuel, am I pushing into that engine? That's going to be what my power input is. So what does that look like in equation form? My fuel power is basically the energy content of the fuel, E, times the flow rate of the fuel. So let's write that down. Let's label these. So the Q here is the flow rate of the fuel. How much fuel is going into that engine? And we can measure that in gallons per hour. We can measure it in kilograms per second. We could use any kind of units that we want to measure that flow rate of the fuel into an engine. This E is the energy content of that fuel. So that's so many BTUs per gallon or kilojoules per kilogram. So it could be measured a couple different ways. So I could do that a lot of different ways. So what we do when we calculate this, we're going to have to understand our units, watch our units pretty carefully, and we'll step through a couple examples here and show you how to do that. So here's the example. Let's talk about this. Here's what we're going to do. So the John Deere 6220, that's one of the tractors that we have in our inventory in the department. And I can look up a sheet, a specification sheet on that tractor, and it tells me that, hey, that tractor uses 4.8 gallons per hour. That's how much fuel that it consumes, 4.85 gallons per hour of diesel fuel, while producing 75.8 horsepower. So it's basically a 75 horsepower tractor, 76 horsepower. So it can produce 75 horsepower, but it takes 4.85 gallons per hour to do that. Find the efficiency. How efficient is that tractor? How much of that fuel energy is it actually utilizing and converting into mechanical energy that I can use? So to do this, we ultimately want this equation up here. We want to look at the power output, which is 75.8, and we want to calculate that ratio to the fuel input power. So we have to calculate the fuel input power first to put into this equation up here. So let's do that. Let's calculate the fuel equivalent power. So the power in the fuel, and I'll write the equation out here, is the energy content of the fuel times the flow rate of that fuel, E times Q, okay? So what is the energy content? I can go back a couple slides where we have that, or I can look this up on the internet or something like that. Let's look at the energy content of diesel fuel. So in our particular case, that energy content, and we'll do English units on this example, since we have the power in horsepower. So that's 129,000, and those units are BTUs per gallon. So 129,000 BTUs per gallon. That's my energy content of the fuel. I have to multiply that now by the flow rate, which is 4.85 gallons per hour. 4.85 gallons per hour. That's my equation. That's all I need to put into that equation, except that now I have to look at the units and get the units to come out the way I want them to be. So what units do I want? I want horsepower. Horsepower, oh yeah, I got to go to that foot-pounds per second kind of a thing and get there. So what do I have in terms of units? Well, I can look right away here, and hey, my gallons will cancel off. So I can cancel off those 2 gallons, and I have BTUs per hour. Oh man, what do I do with BTUs? Oh, wait a minute. We have a conversion of BTUs to foot-pounds. So let's use that. Let's use 1 BTU in the denominator, because that's what I want to get rid of. I put the BTU in the denominator. And 1 BTU, we said, was 778 foot-pounds. Again, this is a conversion that you'll have available on an equation sheet, or you can look it up on the internet if you have to actually do this practically or whatever. But it's a conversion, direct conversion factor from BTUs to foot-pounds. So the BTUs are gone. That's good. I got rid of that. And what do I have? Foot-pounds per hour. And my conversions that I use, depending on which one, let's put that in. Let's put in that horsepower conversion. We know that 1 horsepower is equal to 550 foot-pounds per second. So that was one of the conversions that I had before. So 550 foot-pounds per second is 1 horsepower. So now I've got seconds and I've got hours, so I need to cancel those things off. So I say that I have 1 hour is equivalent to 3,600 seconds. So 60 times 60, 60 seconds in a minute, 60 minutes in an hour, 60 times 60 is 3,600. What's happening to my units? Let's go. The seconds are gone. The hours are gone. The foot-pounds, both of those are gone. Everything is gone except what I want. What I have left is a horsepower. So if we calculate that out and go to multiply everything in the numerator, divide everything in the denominator, we're going to come out to 245 horsepower. So that's the equivalent, that's the power equivalent of the fuel that's going into that engine is 245 horsepower. Now let's calculate the efficiency. We have what we need. So we put that Greek letter eta as the efficiency, like Greek letters. I have fun with that. So that's my power out divided by my fuel power. What is my power out? That was given in the question here. 75.8 horsepower divided by the fuel power, 245. Holy cow, now we start to see those numbers. 245 horsepower. This is an efficiency, so those numbers the units are going to cancel, horsepower cancels off, and this comes out to be 0.305, which I interpret, I can multiply that by 100. That's 30.5%. Wow. Let that sink in for just a second. The equivalent of fuel, power of fuel that's going into that engine is 245 horsepower. What I'm getting out of it is 75.8. So what I'm saying is, of the energy that's going into that engine, only 30% of that energy is actually getting converted to mechanical energy. So it's, in general, a very inefficient system. Where's the rest of that energy going? It's going to heat. It's going to compressing the fuel in that compression stroke. It's going to the intake and the exhaust stroke. We talked about back when we looked at PV curves where some of those losses were. So anything that's heat, as that engine heats up, that's energy that's lost that I have to cool off with a cooling system. Those are all inefficiencies. So when it really comes down to it, an internal combustion engine is not terribly efficient. In this particular example, only 30% of it, and this is somewhat typical. Let's look, okay, that's an older tractor. Let's do another example. Maybe it's a little bit better with newer tractors. So let's look at that red case that we have sitting downstairs. A brand new tractor is only, less than 20 hours on that tractor. So it just came off the assembly line, new technology and everything else. How does it do? So here's the example. Let's do SI units this time so we have some practice. So that Case Magnum 125, it says that it uses 26.37 liters per hour while producing 85.6 kilowatts of power. So that's about 125 horsepower tractor. That's what that converts to. So find the efficiency. Okay, so again, first thing we have to do is find that fuel equivalent power. So the power of the fuel going in is equal to the energy in that fuel times the flow rate of that fuel. So what is the energy? This is diesel fuel. Now we're looking at SI units. So let's do this in SI units. In SI, diesel fuel is 36,000. And the units was a kilojoule per liter. So we can go back to those slides when we looked at fuel properties, or we can look this up somewhere on Wikipedia or something like that to get those numbers. 36,000 kilojoules per liter. Now, I could have written, remember what a joule is. A joule is a Newton meter. That's the same thing. A joule is the same thing as a Newton meter. So what I really could do is write this as a kilonewton meter, and that's going to give me those fundamental units that I'm going to need to get into that power in just a minute. So there's my kilonewtons per meter. So that's my energy content. I'm going to multiply this by my flow rate, Q, which is 26.37 liters per hour. All right, so there we go. That's the equation. That's what I need to plug in. Now I look at my units and say, do my units make sense? What do I have? Well, liters cancel out, so that's easy. Those things are gone. What do I have left? I have in the numerator a kilonewton meter, or Newton meter, so a kilonewton is just 1,000 of them. So I have a Newton meter, and I have hour in the denominator. You remember what power is? In SI units, we're looking at a watt or a kilowatt. Oh, so a watt was a Newton meter per second. So I got to get rid of the hours and go to seconds. So I can say that 1 hour is equal to 3,600 seconds. The hour cancels off, and I end up with, I can multiply this out, I end up with 263, and that's kilonewtons meters per second, which is 263 kilowatts. Same thing as a watt. A kilonewton meter per second is a kilowatt. So there's my power input. That's my fuel equivalent power. All right, you can already see it's not good. 263 kilowatts going in, 85 coming out. All right, let's calculate what that efficiency is, see if it's any better. Greek letter eta here, and I got to do this ratio, so it's the power out divided by the fuel power. Power output in our example is 85.6 kilowatts. Divided by the input power is 263 kilowatts. So the kilowatts cancel off. We end up with the ratio. So this equals 0.325, which if I multiply that by 100, we can say that that's 32.5%. All right, so it's better. The other one was 30%. This one's 32%. And actually, depending on the operating point that you choose for the tractor, it might actually go a little bit higher. But in general, what you find is internal combustion engines, efficiencies are not going to go above 40%. That's about our ceiling. So you're never going to see more than about 40% of your fuel power actually converted into mechanical useful power. Okay, so realizing that, shock factor, right? Wow, these things are inefficient. But at least we have an idea now, and we know how we can calculate those efficiencies. So if I know the flow rate of fuel that's going into that engine, I know something about the energy content of that fuel, and I know what I'm getting out of that engine, now I can figure out the efficiency of that engine. So we could actually do that in a lab, and we will do that activity where we actually measure the efficiency of an engine.